All right, so this is section 1.5 dealing with infinite limits, and really infinite limits pertain to vertical asymptotes, which we've seen in previous math courses. It's just now we're going to give a formal connection with limits. So I drew a picture of a graph, and the function f of x is the green curve, and then you have this red dashed line. And that red dashed line is the asymptote, the vertical asymptote. And since it's a vertical line, always vertical lines have an equation where it's just x equals some value. In this case, it's x equals c. C is where the asymptote occurs. Now, if you see from the right side around c, as x gets closer to c from the right, the graph itself shoots up to positive infinity. For the left side, as the graph of f of x, the green graph, if it gets closer to c from the left of c, it shoots down to negative infinity. And that's the behavior of an asymptote. And these are considered infinite limits. They're one-sided infinite limits. So just to make a comment, last section covered one-sided limits, and for a limit, and then it has x, and then see with the plus sign, that means the limit as x approaches c from the right side. All right, and then the one with c with the minus, this means as the limit, so I'm just going to say quotation marks the same as above, means the limit as x approaches c, this time from the left side. And really, the vertical asymptote is an infinite limit. All right, so it's either x approaches c from the right, if that equals, it's either going to be positive infinity or negative infinity. And then same thing for approaches c from the left, it's either positive infinity or negative infinity. So if this is the case, then x equals c is the vertical asymptote. All right, so pretty much just rewrote what's over here using the notation. And a vertical asymptote is really an infinite limit. So just to recap, if I'm approaching c from the right side, this graph is shooting up to positive infinity. Approaching c from the left side, the graph itself is shooting down to negative infinity. So that infinite limit where it occurs is the vertical asymptote. So here's a theorem that I pulled from the textbook, and it just goes more in specifics on vertical asymptote. It says let f of x and g of x be continuous functions on an open interval containing c. If f of c is not equal to 0, but g of c is equal to 0, and there exists an open interval containing c such that g of x is not 0 for all x not equal to c, then the graph of the function h of x equal to f of x over g of x has a vertical asymptote at x equals c. So this is just formally stating about when a vertical asymptote happens. I will say an important detail is this requirement. Because we've dealt with limits before, where we did limit x approaches c, and it might have been a rational function f of x over g of x, and it might have given something like 0 over 0. And in this case, you had 0 in the numerator, and that's what for f of x, which would be the same as f of c, so 0. All right, and that this would not be a vertical asymptote. This is not a case of that. All right, that's distinction's important. When you plug in c to the top function, it cannot equal 0, but the bottom function does equal 0 when you plug in c. All right, so what I boxed here in green is a strategy that I use for determining vertical asymptotes for rational functions. So given a rational function, so specifically two rational functions, there might be an example that's not a rational function where you can't necessarily apply this. But if it is a rational function, that means you have the numerator is a polynomial, denominator is a polynomial. So both the numerator and denominators are polynomials. All right, and I wrote it in a general structure. You have your leading term ax to the m, and then plus, and I put dot, 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 and you have a bunch of terms that you're adding to the leading term. And on the bottom, you have the leading term bx to the n, and then plus dot, 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 and some other terms that you're adding to the leading term. All right, so it's going to have this structure, a polynomial divided by a polynomial. So the first thing you do is you factor the numerator and denominator if possible. After you do that, you divide out common factors if you can. And then after you do the canceling out of common factors, that's when you set the denominator equal to 0 and solve for x. And then that will give you the vertical asymptotes. The important thing here is that you don't just set the denominator equal to 0 right away, unless you verify that nothing can be factored. Let's say, so verified the function can't be factored or simplified. And okay, so the vertical asymptote, again, it'll be an infinite limit. All right, and that's pretty much the concepts. Now it's a matter of just going through examples. So for this first example, number 4, it says first, or from the graph, determine the limit x approaches 2, and it's got that plus sign, or sorry, approaches -2. So it's going to be x approaches -2 because of the plus sign. That's going to be the right-hand limit. right? And then this has the negative sign above 2 or above -2. That means x is approaching -2 from the left. So you're determining each one-sided limit, the right-hand limit and the left-hand limit. All right, so first I'll take care of the right-hand limit, and I'll use purple. And I keep writing 2 and it's all been -2. So x approaches -2 from the right. All right, so if I have x values that are getting closer and closer to -2, the graph itself in green keeps going off to positive infinity. So we'd say the limit as x approaches -2 from the right is positive infinity. Now approach -2 from the left. Getting closer and closer to -2 for the x values, the y values, so the graph itself goes down forever to -infinity. All right, that's the one-sided limits for this problem. And then you can tell from the graph itself, it has that red dashed line, and that red dashed line is the vertical asymptote. And that occurs at x equals -2. So this is just a common vertical asymptote at x equals -2. All right, that's because the behavior of the graph for the one-sided limits go to infinity or -infinity. Okay, so the next couple examples are going to be determining vertical asymptotes, and for the most part, I will try to do this based off of the strategy I had boxed here. And if you notice number 18, 19, 23, 25, these are all examples where I can apply the strategy because they have polynomials in the numerator and polynomial in the denominator. So all of these are rational functions with the consisting of polynomials only. So since that's the case, I will apply the strategy that I had written earlier. All right, so number 18. So our function is 2 over x minus 3 cubed. Now for this one, there's no factoring that can be done. So there's nothing I'm going to cancel out from top and bottom. So I can go ahead and proceed to set the denominator equal to 0. So go ahead and find the case in which the denominator will be 0. So find x in which case makes the denominator 0. And usually, I mean, you can just kind of observe and just determine x is going to be 3, right? Because 3 minus 3 is 0. Dot denominator. Zero. Okay, so just observing from observation, you can't have, if x were 3, you would have 3 minus 3 is 0. So x equals 3 itself is the vertical asymptote. All right, if you plugged in 3, that's 2 divided by 3 minus 3 cubed. That's 2 over 0. All right, and notice I have 0 in the denominator. But I don't have 0 in the numerator. All right, that's what I was trying to say earlier from this formal theorem about the asymptote, vertical asymptote. F of c can't be 0, but g of c can be. That's the requirement. All right, so that's what we need. Therefore, where in this case c is 3, so x equals 3 is the vertical asymptote. All right, so the next one, 19. All right, so it's x squared over x squared minus 4. So I have a polynomial over a polynomial. So I'm going to see if I can factor, and I can factor the denominator. So the numerator just stays as x squared. The denominator, that's a difference of squares. So that factors into x minus 2 times x plus 2. All right, now there's no common factors that divide out. So I just go ahead and find the cases in which the denominator is 0 for which x values. All right, and really, you can already tell that if I have negative 2, x be 2, that would be 2 minus 2 is 0. 0 times another number is 0. So this x minus 2 factor, it's going to give 2 as the asymptote. The x plus 2, if x were negative 2, it would be negative 2 plus 2, which is 0. So that's going to be x equals negative 2. So these are the vertical asymptotes. And as a comment, just if you plugged in 2 in the whole thing, right, the numerator would just be 2 squared, which is 4. But the point is the numerator would not be 0, whereas the denominator will be 0. And the same kind of thing for negative 2. All right, so number 3. Or sorry, number 23. I think that's what it was. Yeah. So factoring, like if I were to factor the denominator, I find pair of factors of negative 2 that sum up to give me 1, because 1 is the number of coefficient of the middle term. So I know it's going to be x, and x for x squared. I look at the last number, negative 2. What two numbers multiply to give negative 2 that sum up to give me 1? Well, it's going to, I know 1 times 2 is 2. If I need it to be negative 2, and I need the sum of them to be positive 1, then it'll be x plus 2 and x minus 1, right? Because 2 minus 1 is 1. 2 times -1 is -2. And there's no common factors I divide out, so I go ahead and find the x values that make the denominator 0. This one would be x is -2, because -2 plus 2 is 0. This one's going to give me x is 1. All right, and these are the two vertical asymptotes. So really all of this is a review from algebra. There's really nothing new here. So 25's got this crazy looking function. And then the denominator's got 4 terms, and it was x to the 4 minus 2x cubed minus 9x squared plus 18x. All right, so I'm going to go ahead and focus on the denominator for now, and I'll use a different color. So let's, because I need a factor. So I'm going to first focus on factoring the denominator. And whenever I have more than 3 terms, so here I have 4 terms, I would try factor by grouping. So by grouping, I would group a pair. Let's say I grouped those two together, and then the other group, I do those two. And then I factor in each group. Now the x to the 4 minus 2x cubed, the factor is going to be x cubed. Factoring out x cubed from x to the 4th makes x and then minus 2. And then for the other group, we have minus 9x squared and plus 18x. Let's see if I try to do the minus 9 and then also x and see what that gives. So that's going to make this also turn into x minus 2, because -9 times -2 is positive 18. All right, and these should match. All right, so I'm going to factor out x minus 2. So if I factor out x minus 2, what I'm left with is the x cubed minus 9x. But x cubed and -9x have a variable x in common, so I could keep going with this. I could factor out x. So I still have the x minus 2. Now for the x cubed minus 9x, they share x in common, so I factor out x. That's going to make this x squared minus 9. And I'll just reorder it, put x in the front just to make it look nicer, I guess. So it'd be x and then x minus 2, and then x squared minus 9. Now x squared minus 9, that's a difference of squares, because 3 squared is 9. So I have x minus 2. That factors into x minus 3 times x plus 3. All right, so all of this is the denominator. Okay, so just to recap real quick, I factored by grouping. I first grouped in parentheses the first two terms together and the last two terms together. X to the fourth minus 2x cubed had x cubed as a common factor, and that turns into x minus 2 after you factor out x cubed. Minus 9x squared plus 18x share negative 9x as a common factor, and I just went ahead and brought out the negative sign because of the negative 9. So then that makes that also x minus 2 after you bring that out. So then they have the x minus 2's in common, so I factored that out. And that left me with the x cubed minus 9x. Now I could keep going with the factoring because x cubed minus 9x share x as a common factor. All right, so that's what I did next. I factored out x, and that gave me x squared minus 9. I reordered it just so it looks nicer, I guess. So I put x in front and then x minus 2. And then the x squared minus 9 is the difference of squares, so I could factor that. And that's x minus 3 times x plus 3. And then this result is the factored version. And now notice I have 4 factors. And the original denominator had x to the fourth as its leading term. That tells you the maximum number of zeros is what we refer to it, which would tell you the maximum number of factors. All right, so I'm going to equals. Now I'm just going to replace the denominator with what its factored version is. So it was x and then x minus 2 and then x minus 3 times x plus 3. All right, so that's where the green came from doing all of this stuff. So I'll just try to separate this from the rest of the problem. This is kind of like scratch work that you would do to get that. All right, so as a comment, I would expect to see some work to get this denominator. Now, if you don't show work at all and just went from this step to the next step, I would take some points off, and it's a math class, so I need to see some work to prove to me that you know how to do the factoring. So comment, I would need to see all of this factoring. Maybe not done exactly how I do it, but just to prove to me that that's how you got the factors. All right, even if you think it's easy, still show the work. All right, so for the numerator portion, I have 4x squared plus 4x minus 24. All three of those terms have 4 in common, so I'm just going to factor out 4. And that'll leave me with x squared plus x minus 6. And I can keep going with the numerator. So if I factor x squared plus x minus 6, that factors into x plus 3 times x minus 2. So I have 4 times x plus 3 times x minus 2. That's what the whole numerator turns into when it's factored. And then I'll just rewrite the denominator. All right, so notice I have some common factors I can divide out. So the x minus 2's, I can divide those out, and I can divide out the x plus 3's. Generally, I mean, this is just a comment, we would expect a hole in the graph at 2 and negative 3. So that's just a comment. I mean, the question asks for vertical asymptotes, but I just figured I'd add that as an aside to the problems because of the +3's canceling out, and I expect a hole at -3. And then a hole at 2 because of the x minus 2's. So I would expect a hole and then x equals 2. All right, so now the result after I've canceled out the common factors, that's going to leave me with 4 up top. On the bottom, I have x times x minus 3. All right, now I've simplified it as much as I can. So I have the 2 factors. I need to find what 2 values for x and make them 0. Well, if I have just x, you just set x equals 0. That's going to be the vertical asymptote. The second factor, x minus 3, that's going to give you x is 3, because 3 minus 3 is 0. All right, so these 2 are the vertical asymptotes. All right, so that was a problem that required some factoring. All right, so the next problem, number 29. Notice that is different than the previous ones because it involves a trig function. So I might handle that a little bit differently because there's no factoring going to apply. So, and I'm limited on that strategy, but you see that it works for most of the problems. So number 29, f of x equals supposed to be not cosine, cosecant was what I'm supposed to have. Okay, so I'll do this over here. Now notice they don't give us any restrictions on x. So this thing's going to oscillate. You're going to have infinite amount of periods, essentially. So note they don't give us any restrictions on x, meaning that it's not defined in an interval. They don't give us any restrictions on x. So it's going to be periodic, and there's going to be an infinite amount of periods. So there's so that means my answer, if there is vertical asymptote, that's probably going to be more than just 1. It'll be an infinite amount if there exists vertical asymptote. So probably it'll be infinite amount of vertical asymptotes if it exists, which it will. All right, so from trig, you would have to know, so what is cosecant? So cosecant of theta is 1 over sine theta. All right, that's just from trigonometry class. So if I can rewrite this as 1 over sine of pi x. Now notice I have the numerators not 0, but if I want the vertical asymptote, I need the denominator, find x values that make the denominator 0. So I would say numerator is not 0. So I need to find the x values that make the denominator 0 to get the vertical asymptote. Okay. So I need to find x so that sine of pi x equals 0. So if I treat x as theta, or pi x as theta, so if sine theta equals 0, if I'm talking about on the unit circle from 0 to 2 pi, when is sine 0? All right, so that occurs when theta is 0, pi, and 2 pi, right? Because on the unit circle, the points in which it's 0 for sine are at the x-axis. So that's got coordinate 1, 0. This is -1, 0. Start out at 0. I'm at 1, 0. Go pi radians. I end up at -1, 0. And then 2 pi radians. I end up back at 1, 0. Now notice these are multiples of pi. So in general, if I didn't restrict myself to a certain domain, sine of theta will equal 0 when theta equals n times pi. Where n is an integer. All right, you could have negative numbers too if you're revolving it in the opposite direction, going in the clockwise direction. So that's basically, you could have like -3, -1, 0, 1, 2, and 3, and so forth. Those are the values n can be. All right, so that's useful for this. So I kind of thought about, well, when is sine 0 on the unit circle, just in general for theta. And for the unit circle, it only goes from 0 to 2 pi. So the cases in which that happens are 0, pi, and 2 pi, which those are multiples of pi. So in general, if I didn't restrict myself to just 0 and 2 pi, and I went an infinite amount of revolutions, it would be n times pi, where n is an integer. So I'm going to use that fact. So applying this up here, I'll rewrite it. So sine of theta equals 0 when theta is n times pi. In this case, I'm using theta in the place of pi times x. So that means sine of pi x equals 0 when pi times x. All right, that's like our theta equals n times pi. And then I can isolate x by itself by dividing by pi. That means x equals n. That's the vertical asymptotes where n is an integer. These are the values that when you plug them in for x, you get 0 in the denominator for sine of pi times x. So it's an infinite amount of vertical asymptote since they didn't tell us a certain domain for x. Again, so just to recap, and I'm going pretty detailed here. You don't have to go as detailed when you work something out like this. It's just for teaching purposes to understand the content. So it was cosecant of pi x, and you want to find the vertical asymptotes. Well, I used a trig or reciprocal identity that cosecant's 1 over sine. So I just wrote it as 1 over sine of pi x. The numerator is not 0. That's a requirement I need for the vertical asymptote, but I need the denominator to be 0 for whatever x values that make the denominator 0. I need to find the x values that make sine of pi x equal to 0. And I just treated, I kind of treated pi x as theta for a second, and I thought about, well, when is sine of theta equal to 0 in the unit circle? And that occurs at 0, pi, and 2 pi, which are multiples of pi. Then I made it more broad and put it in general terms, that it's sine of theta equals 0 when theta is n times pi. So knowing that relationship, I'm basically treating theta as pi times x. So sine of pi times x equals 0 when pi times x equals n times pi, right? So this is like my theta. And then I got x by itself, so I can determine that what x value to make the denominator 0, and that's when n is an integer. So that's the vertical asymptotes.